what we were discussing last lecture, which was something called the Gram-Schmidt process. We haven't entered into what the Gram-Schmidt process is as of yet. All we did last time was define what orthogonal vectors are, which are vectors whose dot product is 0, which geometrically speaking means that the angle made between these two vectors is a 90-degree angle, a right angle. And then we proved that if you have a set of orthogonal vectors, which means that every vector, when you dot product it with another vector, is linearly is orthogonal, it means that the whole set is a linearly independent set. So orthogonal vectors produce linear independent vectors. And that's what we proved and what we ended with last time. So great. Now we know that orthogonal vectors are linearly independent. So let me just something quickly. Okay. So let's continue with this idea of orthogonality. And so let's start with an orthogonal set of vectors, okay? Let V1, V2, and V3 be an orthogonal set, orthogonal set of vectors. So I should write this as a set. So we have V1. Let's call this 0, 1, 0 as a column vector. V2, 1, 0, 1. And V3 as 1, 0, negative 1. Okay? Now, associated with orthogonality is this idea of normal or orthonormal. So we want to create an orthonormal set of vectors. Now, what does orthonormal mean? So definition, orthonormal means that something is both orthogonal and I would say that a vector or vectors, because we're talking about vectors in particular. It means that vectors are both orthogonal and unit length. And that's what the normal or normalize come from. When we talk about a normal, the second half of this word normal comes from normalize. When you normalize, a vector, that means that you make the vector unit length, meaning that the norm of that vector is 1 because the unit vector is really just 1 over the norm of the original vector multiplied by the original vector. Remember we did this? We talked about normalizing vectors. So if we have a given vector, we can normalize it, meaning that we make it into a unit vector, which means that the length of that vector is 1. And we do so by dividing the vector or multiplying the vector by 1 over the norm of that vector. So for example, if I want to normalize v1, so if I want to normalize v1, I want to get u1. What is u1 going to be? Well, what is v1? V1, isn't it already a unit vector? Isn't v1 0, 1, 0 one of the standard basis elements? And the length of that is just 1. So u1 is just v1, which is 0, 1, 0. So nothing really happened there because it was already normalized from the beginning. Now I want to normalize v2. Now if you look at v2, v2 is 1, 0, 1. The length is not 1. So we have to normalize it. So we have to divide it by, sorry, it should be u. So u's are used for unit length or unit vectors, okay? So we're going to divide this by the norm of v2 and multiply it by v2. What's the norm of v2? What's the norm of v2? Anybody out there? What's the norm of the vector 1, 0, 1? Square root of 2. So then this is square root of 2. So this will be 1 over the square root of 2 multiplied by 1, 0, 1. You can also write this as 1 over rad 2, 0, 1 over rad 2. And if you rationalize it, you can write this as rad 2 over 2, 0, rad 2 over 2. And then if you normalize v3, you get 1 over the norm of v3, v3. So what's the norm of v3? It's very much the same as the norm of v2 because the entries are nearly identical except for one. One of them is negative. But when you find a norm, you also get rad 2. So this equals 1 over rad 2 of 1, 0, negative 1, which can be written as 1 over rad 2, 0, negative 1 over rad 2, and so on and so forth. So now this becomes an orthonormal set. Orthonormal set of vectors. We got 0, originally 0, 1, 0. And then we got 1 over rad 2, 0, 1 over rad 2. Then we got 1 over rad 2, 0, negative 1 over rad 2. And this is a orthonormal set because each of them are orthogonal to one another. If I dot product this with this, I get 0. This with this, I get 0. If I dot product this with this, I also get 0. So they're orthogonal set. And not only are they orthogonal, the ortho part, they're also normalized. So each of these vectors have a length of 1. This idea of orthonormal becomes very useful and necessary for this idea of Gram-Schmidt, the Gram-Schmidt process. Okay. So now that we understand orthogonal vectors, and now when we understand orthonormal vectors, we're going to be now considering orthogonal or orthonormal. I'm just going to start with orthogonal bases. So now these concepts are starting to get blurred together. They're starting to merge, right? We've talked about basis a lot. A basis is a set of vectors that are linearly independent and that span the space. So now we're adding an additional characteristic to a basis, which is orthogonality. So not only are bases that we're going to be considering now set of vectors that are linearly independent and span the space, these vectors also are orthogonal to one another. They're orthogonal, which means that the dot product is 0. So suppose that we have a basis. We have an orthogonal basis. Call it B. And the vectors are V1, V2, all the way to Vn. Okay, so we have an orthogonal basis. And we want to express a vector. Let's call it W in our vector space V, right? We have a vector space. What is that going to look like? So remember, what does it mean for a vector to be expressed? So we want to express a vector W in V using the basis B. What does it mean to express a vector in terms of the basis? What are we looking for? Remember, a basis spans the space. What does it mean to be in the span again of a set of vectors? The coefficients of V to represent W. Right. So then what is that called? Those coefficients come from what expression? It's called the what? We want to express W as a what of the V1, V2, and Vn. It's a two-word phrase. It's 2 words. Linear combination. That's right, Baldwin. You're right. A linear combination. That's what I'm saying in implicitly. I'm saying I want to find W as a linear combination of the basis vectors v1, v2, vn. So in other words, express W as a linear combination of v1, v2, vn. So what does that look like? W is equal to C1V1 plus C2V2 plus dot 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 CN VN. Okay. And then what's the idea? I think Sam mentioned it. The idea is that we can rewrite this as a we can write W as a linear combination of the basis vectors, which entails finding C1, C2, Cn. What are the coefficients of this linear combination expression that gives us W? And then this can be found using a system of equations, which could be represented as a matrix equation, and you can solve for C1, C2, Cn. We've been doing this. We've done this for your exam. Number 2, we know how to do this, right? But there's something special about being orthogonal that makes this problem even simpler. You don't even have to use a matrix equation any longer. You can just use a formula from now on. But it has to do with the fact that they're orthogonal. What does it mean to be orthogonal? It means that the dot product of two distinct vectors is 0. How do you think we can utilize that idea, for example, to figure out C1? And think about the proof that we showed for linear independence from last lecture. For last lecture, we found C1, C2, Cn in a very particular way, right? To show that they're all zeros, to show that they're linearly independent. We used a fact of what it means to be orthogonal. So we're going to use that same fact today for this. What fact is that? If I want to find C1, what would I have to do to this equation? And all you have to do is go back to the proof that we showed last week, and that should give you a hint. A pretty clear hint. Remember what we did in the previous proof? What did we do in the previous proof? We dot product everything with what? We multiplied, yeah, right? We dot product with V1. Now, why did we do that? Why do we dot product with V1? LU composite. No, we're not doing LU right now. We're just multiplying dot product with vectors, because any vector times V1 is 0 as long as it's not V1, right? So because they're orthogonal by orthogonality, right? By orthogonality, V1 dot product with Vi equals 0 if I equals 2 all the way to n. By orthogonality, because I can distribute this all, right? So this becomes W times V1 equals C1 times V1 times V1 plus C2 times V2 times V1 plus all the way to Cn Vn times V1. But this is 0. This is 0. and everything inside here is 0. So what are we left with? We're left with W dot V equals C1 times V1 times V1. Solve for C1. What is C1 going to be? This is W dot V1 divided by V1 dot V1. Wait, but isn't this kind of similar to what we've seen before? Remember seeing this? And if you rewrite this, this becomes W dot V1 divided by V1 norm squared. Do you guys remember this? Where do you guys remember this from? We talked about this when we talked about, that's right, Alexa, projection. This looks very similar. This is actually identical to the projection of a vector onto another vector. So that's what's nice about this, right? Because all of a sudden now this idea of projection comes up, and that's very important. So C1 is the coefficient of the projection of W onto V1. That's what it is. Now, do you see how this is also going to be applicable to every other? It's going to be applicable to every other it's going to be applicable to every other coefficient, not necessarily C1, right? If I want to find C2, what would I have to do? To find C2, what would I have to do to this? What would I have to do to find C2? If I found C1 by dot producting by V1, what would I have to do, guys? Dot product with what? V2, right? Doesn't that make sense? It just seems to follow. If I dot product with V2 instead, the dot product will cancel all the ones that don't have the same vector. So the different vectors, distinct vectors, V2 dot product with anything else than V2 would give you 0. So we get kind of the same idea here. So C2 will be W dot product with V2 divided by the norm of V2 squared. I'm going to write it with the norm. And so you can extend this idea. You can extend this idea for CI. What's CI going to be? The ith coefficient. What would be the ith coefficient? How would I find that? What would be the formula for that? I would have to dot product everything with which vector to get CI? There we go, Alexa. That's right. W dot VI norm of VI squared. That's right. That's it. It's a very convenient reality of having an orthogonal basis, because finding the coefficients for the linear combination of those basis vectors for a given vector, W, it's found quite quickly because now I have the formula for it. If it wasn't orthogonal, then we would have to apply that matrix form of solving equations, which is also not bad either, but this is even simpler. So that's orthogonal basis. And even more specific, I want to know about orthonormal Now, what's an orthonormal basis again? Orthonormal means what? What does the orthonormal mean? A set of vectors are orthogonal and they're all unit length, right? So let B be a set of vectors. I'm gonna call them U now. U1, U2, UN. Be an orthonormal basis where UI dot product UJ equals 0 when I doesn't equal J. And that the norm of UI is 1 when I goes from 1 through N. Express. So let me just say before we do that, right? Let me give you the full thing. So I mean that means that W can be expressed as W dot product V1 divided by V1 squared times V1 plus W dot V2 over V2 squared times V2 plus W dot Vn over Vn squared dot Vn. Or if you make this more compact, more compactly expressed, W is equal to the summation of W dot Vi over the norm of Vi squared times Vi, where I goes from 1 through N. Again, this only works for orthogonal sets of bases. And then when we have an orthonormal, the only difference now is that the orthonormal basis has vectors that are length 1. So if I want to express W, any vector, express W, which is in V, as a linear combination of the basis elements, I should say the basis vectors in V. It's the same idea, right? W can be written as C1 times U1 plus C2 U2 all the way to Cn Un. So not only are they orthogonal, they're also unit length of 1. So then to find C1, right? What would C1 be? How would you get C1? Dot product U1. That's right. When you dot product U1, all of these dot products that are not the same are going to go away, right? And so I'm going to write this find C1. That means I'm going to do W dot U1 plus C1, sorry, U equals C1 U1 plus Cn un. I dot product this with u1. When I dot product it with u1, everything goes away except for cu1 dot u1 w dot u1. And then I can say c1 is equal to w dot u1 over u1 dot u1. But this is equal to w dot u1 all over u1 squared. What's the norm of u1? Because it's a unit vector, it's orthonormal, then u1 is what? Well, we said the norm of u1 or ui for I goes from 1 through n. We said that equals 1. So the denominator becomes 1. So C1 is simply W dot U1. That's it. Wow, that simplifies our life so much. And that's only if you have an orthonormal basis. So orthonormal basis makes our lives a lot easier. So then if I want to find CI, how do I find CI? The ith coefficient. What would CI be? CI would be given by what? The dot product of? How do we find CI? Dot product of UI with W. So W dot UI. That's it. So then what would W look like? W would simply look like the summation of W dot UI times UI. And I goes from 1 through n. Right? So if you compare the two expressions, right, the only difference is the denominator here is divided by the norms of the vector squared, but here I don't have that norm because this is already orthonormal. It's already normalized. It's already a unit vector. Okay, so we know the theory behind this. We know the theory. So let's look at an example. So let's say V1 is 0, 1, 0. V2 is negative 4/5, 0, 3/5. And V3 is 3/5, 0, negative 4/5. Now, what kind of set of vectors do I have here? So B is the set V1, V2, and V3. Is a blank basis. What should I fill in that blank line? What kind of basis would you characterize B as? Is it orthogonal, first of all? If you dot product the vectors with each other pairwise, would you always get 0? It's orthogonal. And then the question becomes, is it all unit length? Are all of these unit length vectors or unit vectors? So 0, 1, 0, definitely unit vector. V1 is unit vector. How about V2? Is V2 a unit? It's not? Well, let's check. What's the norm of V2? It's the square root of -4/5 squared plus 0 squared plus 3/5 squared. Well, what is -4/5 squared? It's 16 over 25. And then 3 over 5 squared is 9 over 25. But when you add 16 plus 9, I get 25 over 25, which is 1. So it is unit. It is a unit. So V1 is a unit, V2 is a unit vector, and V3 is a unit vector by the same reason why V2 is a unit vector. So this is an orthonormal. It's an orthonormal basis. So if this is an orthonormal basis, then let the vector W be 1, 1, 1. Express, or find, I should say, find the coordinate vector of W relative to B. Namely, I want to find this. I want to know what that coordinate vector relative to the basis B is. So how would I proceed? I know W is equal to C1 V1 plus C2 V2 plus C3 V3. So I need to find what C1 is. I need to find what C2 is. And I need to find what C3 is. So how would I go about doing that? Using the dot product. That's right. I have a formula for it because this is an orthonormal basis. Then this is my formula. I just dot product W with the vector. So this is simply W dot product V1. This is W dot product V2. And this is W dot product V3. So what's 1, 1, 1 dot product with 0, 1, 0? Isn't it just 1? C1 is 1. How about C2? Well, it's 1, 1, 1. I'm dot producting it with V2. So if I dot product it, this would be 1 times this plus 1 times this plus 1 times this. But then -4/5 plus 3/5 is how many fifths? -4/5 plus 3/5 is how many fifths? -1/5. That's right. So C3 again, 1, 1, 1. You dot product it with 3/5, 0, -4/5. So you also get the same result, right? C3 is -1/5. So then the coordinate vector W will be equal to what? 1, -1/5, -1/5. So there you have it. The coordinate vector of W with respect to this orthonormal basis. You see how having an orthogonal basis or an orthonormal basis is very convenient, because now finding the coefficients for the linear combination is very easy. It's very easy. We don't have to sweat too much. So any questions so far? Are we good? Yes. I think so. Okay. Now let's take a little pit stop back to what we've been doing so far, right? Um, so we've been used to doing what? Find the eigenvalues. And then after we find the eigenvalues, find the eigenvectors. And then we say, hey, is A diagonalizable? So let's do a little review of this. So how do you find the eigenvalues again of a vector, of a matrix? What do we need to find the eigenvalues of A? Determinant, right? I want to find the determinant of A minus lambda I equals 0. Sometimes people switch the lambda and the A. They do lambda I minus A. Same thing. Same idea. So then this would be what? 4 minus lambda, 3 minus lambda, and then 4 minus lambda again. This is 4, 1, 0, 2, 1, 0. This is the determinant. And I want to set this equal to 0. Okay, and how do I perform the determinant? How do I find the determinant of this matrix? Cofactor expansion in the second column. Very good. Now we're becoming experts at this, right? So I want to do cofactor. And when I do so, I'm going to get what? 3 minus lambda, right? Because that's the entry 2, 2. So it's going to be a positive 3 minus lambda. And then I'm going to cross out the second column, second row, and I'm going to find the determinant of the smaller one. 4 minus lambda, 4 minus lambda, 1, 1. This equals 0. This becomes 4 minus lambda squared minus 1. 3 minus lambda equals 0. This becomes 16 minus 8 lambda plus lambda squared minus 1. And then I get lambda squared minus 8 lambda plus 15. This is 3 minus lambda. And is there anything that multiplies to 8, but that adds to 8 but multiplies to 15? It's gonna be, yeah, -3, -5. So lambda minus 3, lambda plus 5, sorry, minus 5. And there's a lambda minus 3 here, right? If I factor out the negative, this becomes, if I take out the negative from this guy, I get lambda minus 3. So really, this is what I get. I get lambda minus 3 squared lambda minus 5. So I only have two eigenvalues. I got lambda equal 3, and I got lambda equal 5. The algebraic multiplicity of 3 is 2, and the algebraic multiplicity of lambda minus 5, lambda 5 is 1. So algebraic multiplicity equals 1. Algebraic multiplicity equals 2. And then I also want to figure out what is the geometric multiplicity. And what is the geometric multiplicity? And how do I do that? I have to see what happens when you do a minus 3i and what happens with a minus 5i. So then I get, when you subtract by 3, I get 1, 0, 1, right? Across the diagonals, and I get everything else the same, 0, 1, 2, 2, 0, 1. But guess what? When you do the row reduced echelon form, I just have 0, 1, 0. And everything else is zeros. So then this will, what will this give me? This is x1, this is x2, x3. So x1 equals negative x3. x2 is unknown. So I'll call this s, and xt, sorry, x3 is t. So this is negative t. So what's going to be my solution from this? What's my solution? My vector, or the solution to this non-homogeneous system, right? Of this thing here, that vector v is really what? A linear combination of t was of -1, 0, 1 plus s 0, 1, 0. So that means that v is in the span of -1, 0, 1, 0, 1, 0. Right? So these are the eigenvectors of the eigenspace related to lambda equal 3. Now, how about 5? When you subtract 5, you get -1, you get -1. 5, this is -2. You get 2, 2. You get 0, 1. And you get 1, 0. So when you clear things away, you're left with 1, 0, 1, -1, and then you got 2. You can factor everything, you can divide everything by 2. So you get 1, -1, 1, 0, 0, 0. And then when you do the row reduced echelon form of this, what do you get? You subtract the first row with the second row, and you get 0, -1, and then you get -1, Negative times a negative is a positive. So you add 1 to 1, you get 2. You get 2, you get 1, 0, 1. You get 0, 0, and this is negative. Right? That's what you get. So you're going to have a rank 2 nullity of 1. You're going to have 2 pivot variables. And then if you make this a positive 1, this will be negative 2. So you got 2 pivot variables, and you have 1 free variable, which is x3. So you got x1 equals x3, x2 equals 2x3, and x3 is some parameter. So then the vector will be a linear combination, or a scalar, I should say, of the vector 1, 2, 1. Okay, we know all of this, right? So then what is the geometric multiplicity? Well, obviously here it will be 1 for lambda equal 5. And then geometric multiplicity here is 2 because I have two vectors in my basis for the eigenspace. So it matches out. So what happens? A is what? Is A diagonalizable? Yes or no? It is, right? It indeed is. So A is diagonalizable, yes. Because the algebraic multiplicities and geometric multiplicities are the same for each eigenvalue. Okay. So we did a little bit of review with this. But what's the point of this? How is this connected to what we were just discussing? Orthogonal bases and orthonormal bases. Well, it just so happens that if you look at the vectors, right? Look at the eigenvectors of A. What are the eigenvectors of A? I got negative 1, 0, 1, 0, 1, 0, and 1, 2, 1. These come from lambda equaling 3, and this comes from lambda equaling 5. This is a linearly independent set of vectors because they're eigenvectors. Eigenvectors are linearly independent. Because you have 3 linearly independent set in a space that's 3-dimensional, you automatically have a basis. And this basis means that these span R3. So the vectors span is both a spanning set and a linearly independent set. Now the question is the set of eigenvectors a orthogonal set? That's the real question. And the question is, the answer to the question, if a set of eigenvectors is orthogonal, is not always. In this case, it is, but it's not always true. The only thing that it is true is that the eigenvectors, a fact is that eigenvectors from distinct eigenspaces are orthogonal. So if you notice, if you dot product this vector with any of these two vectors or any linear combination, it will always be orthogonal. So the dot product will always be 0. So that's the cool feature of eigenvectors. If you take eigenvectors from different eigenspaces, then their dot product will be 0. So that's very nice as well, of the way that eigenspaces divide up the underlying vector space. It divides it up in such a way where the eigenvectors with respect to themselves are orthogonal if you're in different eigenspaces. But if you're within the same eigenspace, your dot product will not necessarily be 0. So you're not necessarily orthogonal if you're in the same eigenspace for the eigenvectors. But if you're in different ones, then yes, you will be orthogonal. Okay. Okay. Now, once we understand that a bit better, eigenspaces, orthogonality of eigenvectors from different eigenspaces, just the idea of orthogonal, orthonormal bases. Once we have that, then we can go on to the next thing. What's the next thing? We talked about this a bit briefly when we talked about projections, but we're going to talk about it again. The projection theorem. Okay. It states that if W is a finite dimensional subspace, then every vector V in V can be expressed as a sum of W1 plus W2, or I should say W plus W orthogonal. You know what? No, let's leave it as W1, W2, where W1 is in the subspace W and W2 is in the complement, or I should say the orthogonal complement. More specifically, W1 is equal to the projection of V onto W1, onto W. I should write that. Sorry, the other way. It's the projection of V onto W. And W2 is the projection of V onto W complement. So W with that little perpendicular symbol is representing the orthogonal complement of the original W. So it's an orthogonal complement. Now, how can we have a better visualization or understanding of this? Is if I have a plane, okay? Wow, that's not what I wanted. Okay, and I call this plane W. It's the plane. And I have a vector. And I call this vector V. So it's some arbitrary vector in space. So what do we tend to do? We tend to project this vector along the subspace W. And we call this the projection of V onto W. And we're going to call this W1. Now, what's the complement or the orthogonal complement? It's the space that is the orthogonal complement to it. It's something that is orthogonal, perpendicular. So the orthogonal complement will be the line that goes right through it in a perpendicular fashion. So it's going to be something perpendicular to this. So this will be W2. This is the projection of V onto W, orthogonal complement of W. This kind of decomposition of vectors is very common, particularly in physics, right? When you talk about kinematics, and you talk about how a trajectory in space, right? You have a certain vector that associates with that trajectory, and then you can break, or the velocity vector of an object moving in space. You can decompose that velocity vector in its horizontal component and its vertical component. It's the same idea here. Of course, in mathematics, we always generalize this even further, right? We don't say the horizontal component because the subspace doesn't necessarily have to be horizontal. It's just that in physics, we have a horizontal and a vertical component because it's just the way we have our reference, right? Our reference of points of references are with respect to the ground, to the sky, and that's pretty clear. But in mathematics, it's much more generalized, but the idea is the same. So we're taking a vector and we're decomposing it into one of its components being the component in the subspace W, and one of the components being in the orthogonal complement to that subspace W. And so when you add these vectors together, right, W1 plus W2, I indeed get V. I get V back. So that's what the projection theorem states, that if you have a vector and in space and you have a subspace, then that vector V can be written as a sum of two vectors where one of the vectors is in the subspace W and the other vector is in the orthogonal complement to that subspace. Okay? I hope that makes sense. Okay, so if that makes sense, then let W be a subspace of V and B be the set of vectors V1 all the way, I'm gonna write, instead of Vn, I'm gonna write it Vk. Okay, so that means that the dimension of W equals K, not N. And the dimension of V is N. Usually we ascribe not N to the nth dimensional space of the vector space. And we use another letter for W. W could have the same dimension as V, but it could be something less, more than likely. And so then the question is, find the projection. Okay, let this be that, and let V be some vector in V. Find the projection of V onto the subspace W. Well, the way we find the projection of V onto the subspace W is the same thing as saying is equivalent Yeah. I.e., find the linear combination of the vectors in V and B to express W. To express what V is in W. What this is saying, is that to find the projection of V onto a subspace W, right? So if this is a subspace W, and I'm trying to project V onto the subspace, then I can use the basis for W to write it as a linear combination of only those basis elements. So because this is a plane, because I have a plane here, then it's a two-dimensional space, which means that there's only two vectors for the basis of W. So I can rewrite this W1 here, which is a vector in this subspace, as a linear combination of the basis vectors for W. Here we have the basis vectors for W being V1 through Vk, right? And one thing I forgot to mention also is that B was an orthogonal. Let this be an orthogonal set. So they're orthogonal. So if they're orthogonal, then we know that the projection of this vector onto a subspace that has an orthogonal set of basis elements is going to be written as V dot product with W1 over W1 norm squared times W1 plus V dot product with W2 over W2 norm of that squared times W2. And you do this all the way to V dot WN, sorry, V dot, oh, whoops, pardon me. This should be V1. That's going to be a little different here. This is V1, not W. Okay, so the projection of a vector onto a subspace that has a orthogonal basis can be written as a linear combination of those basis elements, which is just really just restating what we found originally for the basis vectors, right? We found that if you have an orthogonal set of basis vectors, then you can express a given vector as a linear combination of those vectors. And that's what we're saying here as well. We're saying the exact same thing. We're saying that if you project V onto a subspace W and that subspace has a orthogonal set of vectors, then finding the projection of that vector onto the subspace is the linear combination of those basis elements that are orthogonal to one another. And we already know what the coefficients look like. They look like this form. Okay, so we're tying things together with projection and orthogonality. We're tying those things together. And what if the set was orthonormal? What would be the only difference for this expression here? There would be norm of V. Well, there would be a norm of V, but it's just you wouldn't write it. The norm of V would just be 1. The norm of these VIs would be 1, so you would just get, you wouldn't see the denominator. It would just be a 1. Okay. Okay. Great. Now, so now we're gonna take this to the next level. Take these concepts and then raise it to the next level. So again, I'm gonna do this little analogy again with the subspace here. So call this a W, right? And then I'm gonna have this vector, call this V. And then this vector here, W1, this is the projection of V onto the subspace W. Now, what is W2? We talked about it being the projection onto the orthogonal complement of W, right? But not to not make everything more complicated with more subspaces, how can we express W2? How can we express W2 if I know what V is and I know what the projection of V is onto W? What would W2 be? Anyone? What would W2 be in terms of in terms of in terms of V and the projection of V onto W? No, nobody? So guys, this is V, right? This is the projection of V onto W. And what we know is that if we add this vector with this vector, I get this vector, correct? So to get this vector here, this one here, that's orthogonal to this one here. Another way to express this is if I take the vector V and I subtract it. It's the same thing as saying V subtracted from the projection of V on W. This little step here is basically what the Gram-Schmidt process is dependent upon or is based upon. So what is the Gram-Schmidt process? What is this Gram-Schmidt? What is this? What is the result? What does it give you? What do we do? What's happening? So the Gram-Schmidt process is the following. The Gram-Schmidt process takes a basis, any basis, and then you give it this basis and you apply the Gram-Schmidt, okay? Gram-Schmidt process. So the result, so it's like almost like a when people talk about functions, right? This is the way like they give you like a diagram like this. So the input to this process is give me any basis. I don't care what it is. When you apply the Gram-Schmidt process on this basis, the output, what you get from it, is an orthogonal basis. That's essentially what the Gram-Schmidt process does. The Gram-Schmidt process takes a basis, any kind, as long as it's a basis. You perform this procedure to it, and you get an orthogonal basis. And that's it. That's all the Gram-Schmidt process is. It takes a basis and makes it orthogonal. That's very powerful, as you can see, because once you have an orthogonal basis, you can write or express vectors very nicely. Very nicely. Finding the coefficients for those linear combinations is very easy. It doesn't become a taxing problem. You don't have to worry about any matrices. You don't have to worry about none of that additional computational element of it. It becomes very easy. Okay, so then what does this process look like? Okay, so to convert a basis, I'm gonna call this B, okay? I'm gonna use the vectors V1, because normally V1s are used for, call it VK. So suppose I want to convert a basis B into an orthogonal basis. And I'm going to use I'm just going to write a different letter, C. And orthogonal basis, I'm going to use Q. Q1, Q2, QK. Okay? So step one, very easy step. Step one is you say, hey, make Q1 equal to V1. That's like the easiest step you'll ever do for this. This is the Gram-Schmidt. This is the beginning of Gram-Schmidt. So to convert a basis into an orthogonal basis, perform the following steps to the Gram-Schmidt process. So what you say is, hey, take the first vector from the basis and make that my first vector for the orthogonal basis. That's the first thing we do. Step two. To find the next one, orthogonal, what I'm going to do is I'm going to take the original vector V1 and I'm going to subtract it from the projection of V1 so subtract it from the projection of V1 onto V2. Pardon me, it's the other way around. The notation is a little bit confusing sometimes. It's V2 onto V1. Now, I know it may seem a little strange at first, but let's see if I can explain this a bit in using a diagram here. Okay, So these red here, these red vectors are v1, for example, v1, v2, and v3. So what did we just do? I said v1 equals q1. Then I'm going to take v2, okay? I'm going to take v2, project it onto v1. What is that going to look like? So this is my projection here. This is the projection of v2. This is the projection of v2 onto v1. But guess what I'm doing though? Sorry, this should be one little thing. This should be v2. What am I doing? I'm taking v2, subtracting it from the projection to get what? To get this vector. And this vector here, this is what? This is q2. Why is this important? Because q2 and q1 are what? Orthogonal. So I'm taking these two vectors that are originally were just vectors that span a certain, these two vectors v1, v2 are spanning a two-dimensional plane, and they're not orthogonal. But by this little process, by step 1 to step 2, by this little process, what I did was I said, okay, so that space that's spanned by these two basis vectors, I'm going to recreate another basis that spans the same space. It's just that now that new basis vectors are orthogonal to one another. So since I can move around the vectors, I can move this over here, right? And then you'll see this a little bit more clearly. This is Q2. And Q2 and Q1 are orthogonal. And do you see, I know it's a little bit hard to see, but this here, these two vectors, if you this spans a certain plane. Q2 and Q1 also span the same plane. They're just orthogonal to one another. Do you guys understand that? Does that make sense? Yeah. So I'm taking vectors, just random basis vectors. I'm taking them one by one. And when I'm taking this one by one step procedure, I take the first vector, make that the first vector of my new basis, which will be orthogonal. To orthogonalize the vectors, I need to subtract off the projection. And when I do that, I create an orthogonal vector with the original, with the vector that I'm using. So Q1 is orthogonal to Q2. Now Q1 and Q2, they span the same plane here as V1 and V2, right? Now the question is, how do I orthogonalize V3? What do you guys think would be step 3? I want to find Q3. I want to find a vector that is orthogonal to Q2 and it is orthogonal to Q1. So looking at step 2, I'm going to repeat the same process again. I'm going to take V3, whatever that is, which is this guy here. And guess what I'm going to do? I'm going to subtract it from what? Yes. It's the projection of V3 onto what though? Onto what? What is this space here? V2, be careful. It's not just V2. So this is when it gets a little tricky. It's in the span of V1, V2. That's the tricky part. Because what's the span of V1, V2? It's the plane. When I project V3 onto this plane, I get this projection here. This is my projection. You see, this is the projection here. This is the projection. But when I take V3 and subtract it from that projection, I get an orthogonal vector to that space, to that projection. It's orthogonal to the projection here, to this space where the projection lives in. Do you understand? So what is this going to look like? V3 minus the projection of this will be what? It's going to be, and the thing is, sorry, this should be Q. Oh, wait. I should mention what this projection is. Pardon me for that. I should mention that this is the projection of not V1 necessarily, but Q1 now. Q1. And this is the span of Q2, Q1 and Q2. Now, what is this going to look like? And that's the reason why we brought up the idea of orthogonal bases, is because the projection of a vector, right? This would be Q1 dot product it with V2 divided by Q1 squared multiplied by V2. V2. Yeah, this is Q1, pardon me, Q1. So again, I'm taking, what am I taking? I'm taking V2 and I'm projecting it onto V1, which happens to be Q1. So I could replace this with Q1 because it's the same thing, Q1. Now, how do you find the projection of a vector onto another vector? It's utilizing this formula, right? Now I'm going to project V3 onto a space that's spanned by two orthogonal vectors. We already talked about that here, right? When you project a vector onto a vector space, onto a subspace, and that subspace is spanned by an orthogonal set of vectors, then the projection is simply this notation here. So what is that going to look like for this step here? It's going to look like V3 dot Q1 over Q1 squared times Q1 plus V3 dot Q2 over Q2 norm of Q2 squared times Q2. And when you subtract it, when you distribute the negative signs, this becomes V3 minus V3 dot Q1 over Q1 squared times Q1 plus, or minus, pardon me, minus V3 dot Q2 over Q2 squared times Q2. That's going to be your new vector Q3. This may appear a bit crazy. I agree. I agree. But if you take this step by step from a three-dimensional point of view, and you see that you're subtracting off of the projection onto a new space, then the result of subtracting a vector from its projection gives you an orthogonal vector. That's the whole point of this. The whole point is that Q1 will now be orthogonal to Q2 when I do this step. And then Q3 will be orthogonal to Q2 and to Q1 if I do this step, because I'm subtracting off V3 from the projection that V3 would look like when you're projected onto this space. So if I project it onto this space and I subtract it from V3 as I'm doing here, the result, this entire result, will be an orthogonal vector to the space spanned by Q1 and Q2, which means that Q3 will be orthogonal to Q2 and will be orthogonal to Q1. And the idea is that you keep this going. Step what? Step K. If I want to find QK, what am I supposed to do? Take VK, subtract it from the projection of VK onto the span of Q1, Q2, and all the way to QK minus 1. That's the idea. So to find a projection of this guy, there's going to be K minus 1 terms. So if I write this out in a shorthand notation, this will be VK minus the summation as I goes from 1 to K minus 1 of VK dot product Q sub I over Q sub I, norm of Q sub I squared times Q sub I. That's going to be the kth step. And the whole point is when you do all of this, when you complete these k steps, then you will produce an orthogonal basis. Yeah, QK would be orthogonal to everything before it. When I mean by everything before it, I'm talking about QK, QK minus 1, QK minus 2, Q3, Q2, Q1. If I repeat this process, the result is that every Q vector will be orthogonal to the previous one, because I'm just reiterating the step of subtracting off projections off of the original vector. You can only really interpret that from a three-dimensional perspective. So it makes sense up until step 3. It makes sense that you're subtracting off projections. But once you start talking about fourth dimension, then it's very difficult to interpret that geometrically or anything above that, right? Anything beyond the third dimension. Doing this makes very little intuitive sense. But the idea is that we're extending this idea of subtracting off projections in higher dimensions. And the idea is that when you do that, even in higher dimensions, the vectors that are produced from subtracting off the projection of the vector is still going to be orthogonal. That's the whole point. All right, guys. Yeah, it is pretty cool, right? It is pretty cool to imagine all of this. And the thing is, what makes this sometimes, it looks complicated is because of the notation, right? And so the notation sometimes can be a little cumbersome or not clear, not intuitive. But if you have the idea, the pictorial idea, the geometric understanding, then all of these notation issues that may arise will be simplified. Okay, so let's see an example in real time now. Let's see how we can apply the projection, the Gram-Schmidt process. So let's find V1. Let's define V1 to be the vector 1, 1, 1. And then V2 will be 0, 1, 1. And then V3 will be 0, 0, 1. Okay, so obviously, are they linearly independent? The answer would be yes. And you can show that many different ways. You can put them as column vectors of a matrix or reduce it and you get the identity. So they're linearly independent. They're 3-dimension in R3. All of them are in R3. So you have 3 linearly independent vectors in R3. You have a basis. It spans. But obviously, are they orthogonal? When you dot product them, they don't get 0, right? You get 2. That's your dot product. V1 dot V2 is 2. So they're not orthogonal. So the basis V1, V2, and V3 is a basis for R3, yet not orthogonal. It's not orthogonal. I want to make it orthogonal. So let's apply the Gram-Schmidt process. What do we do? First step, Q1. What's Q1? Make this into V1. So that's my first step. So that's like where I start. Step 1. Step 2. So once I find 1, 1, 1 as I define as one of the basis elements for my orthogonal set, my second basis element will have to be V2 subtracted off the projection of V2 onto Q1. What is that going to look like? V2 is what? Well, V2 minus V2 dot product Q1 over the norm of Q1 squared times Q1. So V2 is what? 0, 1, 1 minus, what's V2 dot Q1? So V2 is here, Q1 is this one. So when you dot product this, you get what? You get 2. And then what's the norm of Q1? The norm of Q1 is what? 1 squared plus 1 squared plus 1 squared. It's 3. But I'm squaring it, so I don't have the square root. So this is 2/3. And what's Q1? 1, 1, 1. So a lot of this stuff is just subtracting vectors, multiplying vectors. So 0, 1, 1 minus 2/3, 2/3, 2/3. What happens when I subtract? I get negative 2/3, I get 1/3, and I get 1/3. Okay. So then what is Q2? This is Q2. So I got Q1 and I got Q2. Now, what's the idea, guys? What's the idea? The idea is that when I did this step, what's going to happen if I dot product Q1 and Q2? I got to get 0. I just want to check if that's true. So let me dot product 1, 1, 1 with negative 2, right? So I'm going to write this as 1, 1, 1 as a column, as a row, as a comma delimited form. This becomes negative 2/3, 1/3, 1/3. When I dot product this, what do I get? I get negative 2/3 plus 1/3 plus 1/3, 0. It works out. I'm supposed to get 0 regardless when I dot product them. So this indeed is correct. Step 3. To get Q3, what am I supposed to do? Take V3. Subtract it off of what? The projection of V3 onto the span of Q1 and Q2. What does that entail? That entails me subtracting off V3 dot Q1 over Q1 dot Q1 norm squared times Q1 minus V3 dot Q2 over Q2 norm squared times Q2. What's V3? 0, 0, 1. minus. What's V3 dot Q1? Well, what's V3 dot Q1? When you dot product it, you get 1. And again, what's Q1 squared? The norm of Q1 squared. So it's 1, 1, right? We got this already to be a third. And Q1 was 1, 1, 1. So we already got that. And now what's dot product V3 with Q2? So V3 with Q2. When I dot product this, what do I get? Don't I get a third? And now when I find the norm of Q2, what's the norm of Q2 squared? It's just going to be negative 2/3 squared plus 1/3 squared plus 1/3 squared. This becomes 4/9 plus 1/3 plus 1/3, which is 6. Sorry, 1/9. Pardon me. This is 1/9, 1/9. This is 6/9, which is 2/3. So this is 1/3 over 2/3. And Q2 was what? Negative 2/3, 1/3, 1/3. So guys, this does get a little bit computationally annoying with fractions. This is a third, a third, a third. 1/3 over 2/3 is a half. So this is a half. This is negative 2/3. 1/3, 1/3. And then if you have certain things here, let's combine this first. So this becomes negative 1/3, negative 1/3, 2/3. Okay, and this becomes negative a third. This becomes a sixth, a sixth. So then when you add these together, when you subtract them, you add them. So you get 0 on the top. Negative 1/3 minus a sixth. What's negative a third minus a sixth? I get negative 2/6 minus 1/6, which is negative 3/6, which is negative a half. So this is going to be negative 1/2, right? Let me just see. Yeah. And then this is 2/3 minus 1/6, which becomes 4/6 minus a 6, which is 3/6. This is positive a half. This here is Q3. And we have concluded the Gram-Schmidt process. So I took 3 vectors that were a basis for R3 that were not orthogonal. And from those 3 basis vectors, I was able to create a new basis for the same space, just that now they're all orthogonal vectors. And you can check for yourself that if I dot product Q3 with Q2, I indeed get 0. And if I do dot product Q3 with Q1, I also indeed will get 0. So it's kind of like magic. And then the last step, if I want, I can normalize. So now I have, now we have, so after completing the Gram-Schmidt process on B to get C, which is Q1, Q2, and Q3. We can also normalize the vectors in C. So I can normalize them and get a new orthogonal orthonormal set. So U1 would be what? 1 over Q1 times Q1. U2 would be what? 1 over the norm of Q2 times Q2. And then U3 will be 1 over the norm of Q3 Q3 times Q3. The norm of Q1 was a 1 over rad 3. So this would be 1 rad 3, 1 over rad 3, 1 over rad 3. That would be the normalized or the unit vector. What was Q2? Q2 was 2/3, right? So this is going to be 3 halves. And what was Q2 again? Q2 was 0, 1, 1. No, Q2 was negative 2/3, 1/3, 1/3. So when I multiply this out, I get what? Oh, that's my bad. It should be 1 over the square root of 2/3. Yeah, it's the square root of 2/3. So that's the annoying part of this, is dividing this whole thing. So this is the same thing as saying the rad 3 halves of negative 2/3, 1/3, 1/3. So if you find this, you get what? You get negative rad 2 over 3, and then you get 1 over 2 rad 3, and you get the same thing here, 1 over 2 rad 3. And then the last one here, Q3. What was Q3? If you square it, you get, so Q3 is 1/2 squared plus 1/2 squared. Take the square root of that. That's 1/4 plus 1/4, which is 2/4, which is a half. So this is 1 over square root of 2. So then this becomes 1 over square root of 2. This is 0. This is negative a half. This is a half, which is rad 2, 0, negative a half, a half. So when you write this out, this will be 0, negative rad 2 over 2, rad 2 over 2. So these are going to be your orthonormal basis. Will this be on the final? Tune in next time on Dragon Ball. No, I'm just playing.